Hello and welcome back to our third video for week 2 on chemistry. So this is all going to be about water. We're going to talk about water and pH in this last video. So again, just like the other videos, I'm assuming that you have already read these PowerPoints, that you've gone through this material, and I am just going over that higher level review. So again, water is of critical importance. If you think about why, when we're going off to Mars, why are we looking for water? Because if water and life are directly tied together, you are mostly water. Life evolved in water, and it's the properties of water that make life possible. So the biggest thing for this chapter, the number one thing, is to understand what's in this picture right here. That a water molecule is comprised of an oxygen atom and two hydrogen atoms. An oxygen is more electronegative. What does that mean? It means that oxygen is like your mean older brother and is sharing with you, but isn't sharing evenly. So that if you are an electron, you are being shared, going around oxygen once, going around hydrogen, going around oxygen, going around hydrogen. But it's not even. It's not once oxygen, once hydrogen. It's oxygen, 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 hydrogen, oxygen, 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 hydrogen. And what does that result in? It results in the partial charge of each of these atoms. It results in that slight negative hydrogen because the electron, that negative charge, is around the oxygen more. So oxygens have slight negative charges, hydrogens have slightly positive charges. And again, it's that little delta symbol, that little d. You need to be able to recognize that little d, meaning the partial charge. So we've got polar covalent bonds within a water molecule, and that slight positive charge is going to be attracted to slightly negative charges, and that is the hydrogen bond. The hydrogen bond occurs between water molecules, where within a water molecule is a polar covalent bond. What does this mean? All the things I'm about to describe about these properties of water are all because of that hydrogen bonding happening between water molecules. So everything I'm about to review, the question is why? The answer is always going to be hydrogen bonding is the reason why. So let's get into it. So there's a few properties of waters which you will need to understand. The first has to do with the fact that water molecules like other water molecules. If you're slightly positive, you are looking for that slight negative and you guys want to hang out with each other. So what does this mean? This is why you have this, this ability of water to be overfilling a glass. Why? Because water molecules like other water molecules, and it's called cohesion. One water molecule will be attracted to another molecule. And what does this mean? Is that that force of a water molecule with another water molecule can overcome the force of gravity. And you can actually overfill a cup or this water droplet on this penny. You can overfill it because there's attraction between water molecules. The term for the attraction of water molecules to water molecules is cohesion. When water is attracted to a different substance, like a cell wall or the plastic in a graduated pipette or something, we're going to talk about the meniscus curve in the labs, but that's all due to adhesion between the attractive force of a water molecule and something else. And this also explains how a tree that's 30, 40, 50, even higher up, how can water get from the very bottom of the tree all the way to the tippy top to the leaves? It's because of cohesion and adhesion, because those water molecules are going to be pulling each other up. So the force of the very, very top at the very end of those leaves, the water being evaporated and going out to become gas, is actually pulling all of the water up through the trees. So these forces of hydrogen bonding are quite strong, even if each actual hydrogen bond is quite weak. So that's the first property. This is also explaining what happens with surface tension. Those water molecules want to be next to each other, so much so that they can actually overcome that force of gravity up to an extent. Of course, we cannot step on water. Surface tension is not that good. But so the first property of water is thinking about that ability of water molecules wanting to be around each other because of those positive and negative partial charges. The next property of water you need to understand has to do with energy. And we're going to talk a lot more about energy in chapter in week 5, I want to say. But here was just our first introduction to thinking about heat. Why is something hotter and colder? Not because of any crazy properties of the thing inherently, but rather because of the motion of the molecules that are making up that matter. And so something that is hot is moving faster. Those molecules are bumping into each other and moving faster. That's higher temperature. And how this relates to water is the fact that water is held together by a whole bunch of hydrogen bonds. And so it's got a very, very high specific heat. What does that mean? It means that to increase the temperature of water by a little bit, you need to add more energy as compared to other molecules, other elements, other compounds. So water, as you can see right here, is the highest here because you need to add a lot more energy to water to change its temperature. Why? Because heat is being absorbed when hydrogen bonds break, and heat is released when hydrogen bonds form. So water molecules bumping into each other are constantly making and breaking hydrogen bonds instead of increasing their motion. So if we can think of this question, why does it take a long time for water to boil? Because you need to add a whole lot of energy so that you're not just making and breaking more bonds, but that those water molecules themselves are actually moving faster and increasing their temperature. Whereas the metal on your pot has a much lower specific heat. The amount of energy it takes for those metal atoms to keep moving faster and faster is a lot less. So you can burn yourself on a pot while your water is still just lukewarm. This process, again, about thinking of making and breaking hydrogen bonds is how we can explain why getting wet makes you feel cooler when you're outside on a hot day like today. Why? Because there is energy that is going to go to have that water molecule increase its motion enough to become a gas. And the energy that is used to do that gets taken from the source. So your skin gets cooler when you are wet, and the energy from your skin is transferred to that water molecule to go off and become gas. This is also how evaporative coolers work in homes here in Arizona. Another key aspect of water and these hydrogen bonds is the fact that hydrogen bonds will keep making and breaking in liquid water. They're making and breaking, moving all around, whereas in ice, when those water molecules have less energy and are moving around less, they're going to structure themselves in a particular way in this particular lattice to ensure that the slight positives are only near slight negatives. So you form this lattice work that actually takes up more space than when water is just liquid. And this is really rare. Almost every other thing on Earth, if you cool it down, is going to become more dense. But water, based on these hydrogen bonds, that is not the case. And that's quite good because, again, life wouldn't have evolved in the way it did, and it wouldn't have been able to exist if our lakes froze from the bottom up and stayed solid. So these are really important. I love this video, so I hope you watched it, thinking about those water molecules moving. Last key thing for water, or why we care so much about water, or why does water get its whole own PowerPoint, is because water is really important as a solvent. So you need to know the terms solution, solvent, solute. The solvent is like the liquid, the solute is the thing that's being dissolved. And water is an excellent solvent because of all those hydrogen bonds, because of those partial charges. What water will do is it will break up compounds that are salts, compounds that are going to be releasing ions because a water molecule will literally pull them apart. So if you had a salt where you have all this sodium and chloride next to each other, the water molecules will literally pull apart each of those atoms, and they will be surrounded in the orientation where a negative charge is going to be surrounded by those slightly positive hydrogens, and that positive sodium is going to be surrounded by those slightly negative oxygens. Again, I highly recommend watching this video that will also review this material. This works for salts. It also works for larger molecules. So we're going to talk a little bit about the solubility of different molecules later on in the class, but it's not just salts. You can dissolve, as we know, sugars. We all like to put sugar in our coffee or tea. Water will also wonderfully break apart anything that's got those ionic charges or just significant partial polar regions. And we've got specific terms. We've got the term hydrophilic, meaning water loving, and we have the term hydrophobic. This is one of those where thinking about the root word can actually really help you. If the word phobic is like a fear, most times in class I'd ask you if anyone knows a crazy weird word that ends in phobic. Usually arachnophobia people have heard of, or claustrophobia. Phobia is something you're scared of. Philic is something you like. So if you're hydrophilic, that means water likes you. And the only reason water likes things is because of charge. It has nothing to do with how nice you are or what you look like or what the molecule is. The only thing that water looks at is charge. If you have charge, water likes you. If you don't have any charges, water doesn't like you. So if we think about why don't oil and water mix, it has nothing to do with density. It has to do with the fact that water is filled with partial charges and is going to want to be around other things with partial charge. Whereas oil, which we'll talk about more in a little while, is a hydrocarbon. Oil is mostly carbons and hydrogens, which bond nonpolar. Carbon is nice, evenly sharing all of its electrons. So oil and water don't mix because water is looking for charge and is going to hang out with its fellow water molecules and basically completely ignore all those nonpolar hydrocarbons. So how would you clean a greasy bicycle chain? Would you use water or gasoline? You would want to use another nonpolar solute. So you're going to use, solvent. You're going to use something else that is nonpolar. Water would be attracted to charge and is going to dissolve things with partial charge. So then the very last thing that we're going to review for this chapter is pH and acids and bases. So you need to know that an acid is any substance that increases the hydrogen ion concentration, and a base is any substance that's going to reduce the hydrogen ion concentration. Now I hope you went through this and thinking about the mathematics of the pH scale, which is the concentration. It's the concentration of hydrogen ions. It's how we talk about pH. It's how we talk about that acids and bases. And I'd like you to understand the math of this, but overall, if you don't, you just need to understand some key things. That it's a log scale. The log scale means that it's going to be 10 times as you go up the number of 1. The difference between 4 and 5 isn't actually 1, it's 10. And it's also, there's some exponents involved. So what does that mean? It means that if a pH is 2, that means that the concentration of hydrogen ions in that solution is 10 to the minus 2 moles per liter. If you write that number as a decimal, and when you have an exponent to the negative 2, you're going to move that to the left by 2. So that's 0.01 moles per liter. But a pH of 5 is going to be 10 to the minus 5. What does that mean? You're going to move that decimal place over 5. And if we do this for pH of 9, it's going to be 10 to the minus 9. You're going to have 8 zeros. pH of 13, you're going to have 10 to the minus 13, or again, 12 zeros. So if you think about which was a bigger number, even though these are all small numbers, you would rather have 0.01 milliliters versus 0. Blah, 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 however many zeros, that's 12 zeros, 1, if it was something that you really wanted, right? So this is a larger number than this, even if they are both very small numbers. So this is explaining why As your pH goes up, the pH of 13 has fewer hydrogen ions than a pH of 2. So again, a low pH is an acidic solution and it has more hydrogen ions than the basic solution. A neutral solution, based again on our log scale, is 7. So a neutral solution has a pH of 7. So your pH of 7 is where you have an equal concentration of hydrogen ions and hydroxide ions. So H equals OH. So these are equal. That's neutral, and that's at 7. Anything below 7 is going to be an acidic, it's an acid. There's more hydrogen ions. And anything above from 7 to 14, that's a basic solution. Then the very last thing we're going to just touch on are buffers. Buffer is something that can either take up those hydrogen ions or give up hydrogen ions. So they work to keep that pH constant. And this is really important in our bodies to make sure that our pH doesn't change, because we'll see pH affects how enzymes react. And then this slide was just to also think about how these ideas actually apply in life. So if we think about what is increasing carbon dioxide concentration in our air, how is that going to affect solutions? That effect of adding carbon dioxide to water actually ends up in producing hydrogen ions. And increasing a hydrogen ion is by definition making something more acidic. So when we add a lot of more carbon dioxide to the atmosphere, inherently, based on chemistry, we are going to be increasing the acidity of our oceans. Okay, so our last topic for this week is not actually in this section. It's actually in the next chapter, chapter 3.1, but I wanted to include it here because it's a nice contrast to everything we just learned about and those polar covalent bonds pulling the electrons from hydrogen to the oxygen, making oxygen more negative and those hydrogens more positive. So those are those polar covalent bonds which make those hydrogen bonds between the water molecules. So the exact opposite to those polar covalent bonds are the bonds that carbon forms. So we're going to see in the next section, carbon is the magical element that basically all of our life molecules, our macromolecules, are based on. And the key, or one of the key attributes of carbon, is that it's nonpolar. Again, carbon shares evenly its electrons, so there's no partial charges. The other key thing for carbon, with its 4 valence electrons, it needs 4 more electrons to fill that valence shell, giving it that perfect octet. It does that again by forming 4 covalent bonds. So carbon will always have 4 lines coming out of it, which each line representing a covalent bond, which again is the sharing of 2 electrons. But the thing that makes carbon sort of, it's not unique, but one of the specialties about carbon is that it forms these covalent bonds so that they're strong, but they're not extremely strong. They can be broken. So we'll talk more about the energy that's stored in those carbon-carbon bonds when we're doing aerobic respiration. But what you can see with those 4 bonds is that there's lots of different shapes carbons can form. So carbons and hydrogens make hydrocarbons, and there's a lot of different forms that they can come in. In the next chapter, we're going to talk about isomers, but just understand that you can have carbon skeletons that are short or long. You can see ones later that will be much longer. They can be unbranched or branched. And again, in the next section, we're going to talk about where we different molecules where it just has to do with where the carbons are coming off of them. And the other thing is they're always going to have 4 bonds, but sometimes they're not going to be shared with 4 different atoms, but rather they're going to form double bonds or even I don't have a triple bond on here, or even triple bonds, which aren't, again, labeled here. So you'll always have 4 lines coming off of carbon, but sometimes they might be together or they might be to 4 different atoms. And again, we're going to see that carbon can also, it can form these nice little rings that we'll see in the next section. So that's the layout of carbon and these nonpolar bonds. The thing about those nonpolar bonds is to remember, again, for all atoms, is that these are physical things that have shapes. And so depending on if there's single bonds or double bonds, it's actually going to form a different physical structure with a different 3D, three-dimensional relationship to how that looks there. So the last thing, which is the most memorization you're going to have, is these functional groups. So carbons are mostly hydrocarbons I showed you before. Those molecules of life we're going to learn about next have these different functional groups attached to those carbon-hydrogen molecules. The short thing to tell you right now, you need to memorize all of these. And unless you're currently taking chemistry, there's no way that you already know this information. So I would highly, highly recommend getting out a piece of paper and just copying them down first by looking at them and then trying to make this sheet on your own. Make your own flashcards, test yourself. Because I, from now on, and will forever expect you to know that a hydroxyl group is when you have an oxygen and a hydrogen connected to anything. This R represents anything. It's like a variable X. So most of the time we're going to see in this class that R is going to be carbon. So when you've got an oxygen and a hydrogen, that's a hydroxyl group. And just like we talked about, the oxygen pulling those electrons, that's going to be polar. The methyl group is going to be non-polar. You got the carbonyl, it's pronounced carbonyl. In my head, I think of it as carbonly because it's got just that carbon with a double bonded to an oxygen. It can have anything on these two sides, and that's still a carbonyl group. But when it's a carbon with that double bonded oxygen and a hydroxyl group, it is not referred to as a carbonyl and a hydroxyl, but rather the whole thing is a carboxyl group. And we're going to see this particularly in amino acids, but you'll need to be able to recognize that carbon, double bonded oxygen, and hydroxyl, it's not two separate functional groups, it's one that's the that's the carboxyl group that's made up of those two functional groups. But this is important because it actually ends up being more than just polar, but rather charged, as basically the hydroxyl group will give away its hydrogen and end up with a negative charge. The other functional group that's important for amino acids is this amino group that you'll need to recognize by that N with amino, and hopefully you can remember that. And then again, the last two that you need to recognize are phosphate groups and the sulfhydryl groups. The sulfhydryl groups will also come important because those are going to interact with each other in proteins. So you need to be able to recognize the functional group, the structure, and the properties of these different molecules. So trust me, don't wait till next week. You've got a lot to learn for next week. Start your working on learning these functional groups. And with that, we are finished with week 2. And that is the end of week 2 material.